The James Webb Space Telescope is the most delayed in the history of telescopes and is almost the most expensive. However, these two attributes have only increased expectations for the observation station and astronomers as they get nearer to delivering. It plans to uncover many of the universe's secrets, but one of these discoveries stands out because it changes everything, and here we start talking about the warp bubble. What is the warp bubble, and how will the James Webb Space Telescope help discover it? Stay tuned to find out. The James Webb Space Telescope is an amazing and novel piece of engineering that required lots of ingenuity during the design, fabrication, assembling, and most importantly, the launch. The NASA team and their partners had to be extra careful because, unlike the Hubble, for instance, they only got one chance to launch the JWST with all of its complexities, and if anything went wrong, it simply meant the mission failed. Mission failures means the loss of tens of billions of dollars and countless working hours. The JWST is now in orbit 1 million miles away and so far out in space that NASA can't send engineers to fix any issue. The Hubble is much closer to orbiting the Earth at 547 kilometers, and astronauts have even paid it a visit to correct some errors that came up. But for the JWST, not even refueling is certain at the moment unless NASA comes up with a technology that can make that possible. The JWST is a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. It is an infrared telescope that can peer further away into space and further into the past than any previous telescope. The engineers chose infrared light for several reasons. First off, infrared light can pass through cosmic dust without scattering to the same extent as visible light, and the second reason is the phenomenon referred to as redshift, which means as the universe expands, light is stretched from visible wavelengths to the infrared spectrum, and as such the telescope can see more distant destinations. Because of the immense size of the universe, redshifting allows us to see further into the past, exactly 13.5 billion years to be precise. At its location, it will hide in the Earth's shadow to minimize exposure to heat from the trio of the Sun, Earth, and Moon. This protection from heat is so critical that NASA designed a special shield made of 5 layers made from a special material. Each layer is the size of a standard tennis court and had to be folded up or the telescope wouldn't fit in the launch vehicle. The shields had to be unfurled and precisely positioned to align or they wouldn't work at all, and the goal was to prevent interference with the heat-sensitive components on board. The primary mirror of the JWST was the biggest of any space telescope, and it too had to be folded for the launch. NASA had this in mind when it designed the mirror to be composed of 18 different hexagonal segments and 6.5 meters in diameter. However, while larger than the Hubble, the JWST is lighter as it weighed 14,300 pounds on Earth, while the older telescope weighed 24,500 pounds. Currently, engineers are working on the 4th stage of the long process to align the James Webb Telescope mirrors, according to a new statement from the agency. The observatory's new infrared spectrograph near SPEC instrument has finished initial checkout, and its 3 key mechanisms have successfully been characterized. The statement noted the instrument will allow Webb to study the fingerprint of light of up to 100 galaxies, giving scientists crucial information about mass, temperature, and chemical composition. Earlier, the team corrected the positions of Webb's primary mirror segments and updated the alignment of secondary mirror to bring the 18 individual images into focus, then stack the 18 images to produce one unified image. JWST will be able to observe our home planetary system, as its great sensitivity will enable the identification and characterization of comets and other icy bodies in the solar system's outermost regions. In such a remote location, these objects are largely unchanged since their formation and may contain clues to the origins of Earth, particularly the source of its water, which may be a result of the bombardment by such bodies early in its lifetime. However, few discoveries made by the JWST will come close to the warp bubble because it's going to change absolutely everything. What exactly is a warp bubble? In simpler terms, a warp bubble is a bit of space that is contracted in front and expanded in the back. The contraction and expansion, theoretically, push the bubble and its components forward at speeds surpassing the speed of light without ever violating the laws of physics. When one travels using a warp bubble, you are actually not technically traveling faster than light, you are only surfing a bubble of condensed space. Why is there so much hype around the warp bubble? The reason is that they eliminate a major problem of faster than light travel, time dilation. For instance, let's say you actually managed to travel faster than light. Everything else outside of your craft would speed up, meaning that the 3-hour tour you took to a nice tropical planet could have equaled 2 years of time passing on Earth. Put simply, if you plan to move faster than light while following the known laws of physics, you would better say goodbye to everything you've ever loved before heading out. However, the warp bubbles get around this problem because the space inside the bubble remains unaffected. So an hour of travel spent traveling at warp speed would mean that only an hour would pass for everyone else not currently in your warp bubble. What are the real-life implications of warp bubbles? Let's take a look. The closest star to Earth, Proxima Centauri, is about 4.25 light-years away, about 25 trillion miles or 40 trillion kilometers. The fastest ever spacecraft at the Parker Solar Probe will reach a top speed of 450,000 miles per hour. If it heads for Proxima Centauri at that speed, it would take about 663 years to reach the destination. Still, with warp bubbles, one could theoretically get to Alpha Centauri in a month as measured by clocks on the spacecraft and clocks in mission control. Warp bubbles were long the domain of science fiction until theoretical physicist Miguel Alcubierre came along and theorized his Alcubierre warp drive in 1994, which maintained general relativity while allowing for faster-than-light travel. Alcubierre's warp drive would work by creating a bubble of flat space-time around the spaceship and curving space-time around that bubble to reduce distances. The warp drive would require either negative mass, a theorized type of matter, or a ring of negative energy density to work, but since physicists have never observed negative mass, we are left with negative energy as the only option. To create negative energy, a warp drive would use a huge amount of mass to create an imbalance between particles and antiparticles. For example, if an electron and an anti-electron appear near the warp drive, one of the particles will get trapped by the mass, resulting in an imbalance. This imbalance results in negative energy density. Alcubierre's warp drive would use this negative energy to create the space-time bubble, but for a warp drive to generate enough negative energy, you would need a lot of matter. Alcubierre estimated that a warp drive with a 100-meter bubble would require the mass of the entire visible universe. In 1999, physicist Chris Vandenbroek showed that expanding the volume inside the bubble but keeping the surface area constant would reduce the energy requirement significantly to just about the mass of the Sun. This is a significant drop in the requirement, but for practical purposes, where do we get the mass of the Sun to expend on a single trip? All hope is not lost though, as we might be able to do away with all these prohibitive requirements, according to research by physicist Eric Lentz. By examining the assumptions leading to the negative energy requirements in Alcubierre's work, his colleague Lentz began by analyzing space-time, modeling the multi-dimension substance as a stack of very thin layers. He found that Alcubierre had only considered comparatively simple linear relationships between the equations for shifting one layer onto the next, but Lentz chose more complex hyperbolic relations which typically express rapidly changing quantities. This resulted in a different warp bubble than the one obtained by Alcubierre. Of course, Lentz's warp bubble still requires enormous amounts of mass and energy, but only positive amounts according to his calculations. So, are you excited about the warp bubble, and do you think the James Webb Telescope could make warp travel a possibility? Let us know what you think by leaving a comment in the comment section below. Don't forget to subscribe, and we'll see you in the next video.